In 1874, a German mathematician proved that some infinities are bigger than others. His colleague called him a corrupter of youth. Mathematics has never quite recovered. Let's start with something deceptively simple. Counting. You learn it as a child. 1, 2, 3, 4, and so on. The natural numbers go on forever. That's infinity. Everyone agrees on this. But here's where it gets uncomfortable. How many even numbers are there? Your gut says half as many as the naturals. Your gut is wrong. You can pair every natural number with an even number. 1 pairs with 2. 2 pairs with 4. 3 pairs with 6. Every natural has a partner. No even number is left out. The two sets are the same size. Infinity is not a number. It's a way of matching things up. George Cantor was born in St. Petersburg in 1845 and grew up in Germany. He was brilliant, devout, and possessed by a single question. How big is infinity? Not philosophically. Precisely. He wanted to measure it the way you measure a table. His colleagues thought this was either genius or insanity. History would eventually decide it was both. Leopold Kronecker was everything Cantor was not. Established. Wealthy. Politically connected. He sat on the editorial boards that decided whose papers got published. And he had a very firm opinion. God made the integers. All else is the work of man. That's a direct quote. To Kronecker, infinity was a useful fiction. A shorthand. You could talk about it, but it didn't actually exist. Cantor was about to prove him spectacularly wrong. Cantor's first trick was the rational numbers. Fractions. 1/2, 3/4, 7/10. There are infinitely many fractions between any two whole numbers. Between 0 and 1 alone, there are 1/2, 1/3, 1/4, 1/5, and infinitely more. Surely there must be more fractions than natural numbers. Cantor said no. He arranged every fraction into a grid. Numerators along the top, denominators down the side. Then he drew a zigzag line through the grid, hitting every fraction exactly once. 1, 2, 1/2, 1/3, 2, skip the duplicates, 3, and onwards. A single path that visits every rational number. Which means you can list them. Number them. Count them. The rationals are countably infinite. Same size as the naturals. This was unexpected. But it was the next result that started the war. Now for the real numbers. Every point on the number line. Every decimal that goes on forever. Pi. The square root of 2. 0.3333, repeating. Cantor asked, can you list them all? Suppose you can. Write down a list. First real number, second real number, third, and so on. Every real number between 0 and 1, each written as an infinite decimal. Now, Cantor builds a new number. Take the first digit of the first number and change it. Take the second digit of the second number and change it. Take the third digit of the third number and change it. Go down the diagonal, changing every digit. The number you build is different from the first number in the first digit. Different from the second number in the second digit. Different from every number on the list in at least one place. So it can't be on the list. But we said the list contained every real number. Contradiction. The list cannot exist. You cannot count the real numbers. There are more of them than there are natural numbers. Infinity comes in sizes. And the infinity of the reals is strictly, provably, irreducibly bigger than the infinity of the naturals. Kronecker was furious. This wasn't mathematics, he said. It was theology. He blocked Cantor's papers from journals. He lobbied against Cantor's promotion. He told anyone who would listen that Cantor's work was a disease infecting mathematics. A disease. His word. Cantor, already prone to depression, spiraled. He wrote desperate letters to colleagues. He tried to leave mathematics entirely, applying for a position in philosophy. He was rejected. The mathematical establishment sided with Kronecker. Infinity was too strange. Too unsettling. Better to pretend the diagonal argument didn't exist. But Cantor kept going. He gave the infinities names. Aleph null, the smallest infinity. The size of the natural numbers. Aleph 1, the next infinity up. He proved you can always build a bigger infinity by taking the power set, the set of all subsets. The power set of the naturals is strictly larger than the naturals. The power set of that is larger still. An infinite tower of infinities, each one dwarfing the last. It's infinities all the way up. And he wondered, is there anything between aleph null and the continuum? Between the infinity of counting and the infinity of the real line? He believed the answer was no. He called this the continuum hypothesis. And he spent the rest of his life trying to prove it. He couldn't. The proof wouldn't come. Year after year, attempt after attempt. In 1884, Cantor suffered a severe mental breakdown. He was admitted to a sanatorium. He recovered, returned to work, and broke down again. And again. He spent his final years in and out of institutions, convinced that Francis Bacon wrote Shakespeare's plays, writing letters about set theory to no one in particular. He died in 1918, in a sanatorium, malnourished. The greatest set theorist who ever lived, defeated not by mathematics, but by a single question he couldn't answer. And then mathematics changed its mind. David Hilbert called Cantor's work the finest product of mathematical genius and one of the supreme achievements of human intellectual activity. Bertrand Russell built his entire logical framework on Cantor's sets. Zermelo and Frenkel formalized set theory into the foundation of all modern mathematics. Every proof you've ever seen rests, ultimately, on the ideas that Kronecker called a disease. But the continuum hypothesis? In 1940, Kurt Gödel proved you can't disprove it. In 1963, Paul Cohen proved you can't prove it. It is independent of the standard axioms of mathematics. Not true. Not false. Undecidable. Cantor spent decades trying to answer a question that mathematics itself cannot answer. The universe of sets doesn't care whether there's an infinity between the countable and the continuum. It works either way. So here's what Cantor left us. Infinity is not one thing. It's an endless hierarchy. Some infinities are countable. Some are not. Some questions have no answer, and that itself is an answer. And one man's madness turned out to be the foundation of everything we now call rigorous mathematics. Kronecker died in 1891, remembered as a number theorist. Cantor died in 1918, remembered as a revolutionary. Sometimes, the corrupter of youth is just ahead of schedule.